specifically as the science advisor for Star Trek, which is keeping the science honest in Star Trek. Here's Erin Macdonald.
All right. Hi, everyone. I brought a show and tell, and I broke everything, so we're going to hopefully get it set up soon. It's ready to go, but I'm happy to kind of vamp. I'll at least tell you a little bit about me and what I'm hopefully going to talk about. So as Mark said, I was like, Mark Okren, everyone, that's like a big deal. I did my PhD in astrophysics, specifically in gravitational waves and space-time general relativity stuff. And if we can keep, is this going to turn to my laptop at some point? Okay. I have so many good videos I want to share. But yeah, so this is my first time at Farpoint, which I'm thrilled about. Yes, I am. Thank you. I have heard many wonderful things about this convention over the years, so I was very honored that they invited me and are having me here. But yeah, so my background is in general relativity and gravitational waves. I left the LIGO collaboration a year before their Nobel Prize-winning detection, which is fine, but if you see me at the bar, you know why. No, it's all good. I helped loosen the jar lid. That's kind of my official statement. But yeah, it's been a journey. I know everyone kind of asks how I got from, it's been a long road, getting from there to here. Just walked myself into that one. But yeah, so I was working in academia for a while, and then I left and went into science communication, working at museums and community college. And then I transitioned into aerospace engineering, but I really missed teaching. So I started coming to conventions like these and talking about the science behind science fiction. Everything from Star Trek to Star Wars to Mass Effect, video games, all those fun things. And then I ended up going to Los Angeles. And I started working, I was still working as an aerospace engineer, but I transitioned, and CBS heard about my physics of Star Trek talks that I had been giving for like 10 years at that point, and invited me to come to their licensed events, which kind of got me on their radar. And then for season 3 of Star Trek Discovery, Michelle Paradise took over as showrunner, and she wanted to have a scientist, multiple scientists on staff. And so I was on their radar. I interviewed for the job, and she brought me on as astrophysicist. Some of you also might know Professor Mohammed Noor was brought on as the biologist, which we had known each other independently from conventions. And then she was like, oh, we hired a biologist, this guy from Duke, Professor Mohammed Noor. I was like, Mohammed! I texted him, like, oh my God, we're doing this together. And so I've been involved since season 3 of Discovery. I was not involved on season 1 of Picard, and I wasn't involved on season 1 of Lower Decks. But everything other than that, I have been the official science advisor for Star Trek basically since late 2019. So I'm now heading into my 5th year of that, which is crazy. Yeah. Okay. Can we test this? I saw the screen go blinky blink, so I don't know if it's plugged in. But I want to show stuff. Stand by. Does anyone have any questions? I'll repeat them. Yeah.
So have you ever watched, whether it's an old Star Trek or another old sci-fi show, and with your knowledge just been like, oh God?
So I'm a big sci-fi fan anyway, so I'm pretty easy to please, and very few things will make me really cringe. And what I always say is, like, my job is to just make sure people don't say anything wrong. You want to yes and science as much as you want, I will probably let it go. But if you, like, get something obviously incorrect, that's when I'll get real sad and angry. And I was watching the Netflix reboot of Voltron, which had great, weirdly great space-time science, like the energy, the warp, they're faster than light travel, like all of it was so good. And then, like, later on in the season, they were like, we've made it home to our star system, the Milky Way. And I was like, oh no! And I burst into tears. I was really sad. So that's the one that lives in my brain.
Thank you.
Forever, yeah.
Yes. Hi, I was wondering what took you all the way to the University of Glasgow for your PhD, and does it have anything to do with the surname Macdonald?
Just a wee bit. Yeah, so my grandfather was the one who immigrated, so it wasn't that far ago. I say that, but he was also born in 1890, so I have like 2 generations. It's very weird. So we went back when I was a kid and got to see where my family was from, and it was close enough that like they remembered, literally like that was your family's house. And I loved it. I loved the culture. I loved the life in Scotland, and so I always wanted to live there at some point. I never got a chance to study abroad because I was crunching degrees, and so I knew I didn't want to like be a professor. So it wasn't as important to me like staying in the United States to follow that track. And the PhD system in the UK was much more suited to my background in the sense that I went to the University of Colorado Boulder for my undergrad, which is a hard undergrad research program. So I'd been doing research since I was a sophomore in college, and I had published a paper, and like I was really comfortable doing research. And the UK graduate programs are more like apprenticeships. Like you show up and they're like, there's your chair, see you in 3.5 years with a PhD. And I was like, okay. But it was great. University of Glasgow was a fantastic experience. I would move back in a heartbeat. I loved living in Glasgow, and they embraced me. And I just love that after living overseas for so long, which ultimately total it was 5 years, including my postdoc in Wales. But it's like Ronnie's going to be at the 3 Judges at 7 o'clock now, probably. So like just being able to kind of have that life was really special to me. And also Scotland got completely robbed in the rugby today. If anyone watched it, I was so angry. It's fine.
Where in Wales were you? 'Cause I studied there also.
Oh, cool. Yeah. I was at Cardiff University. I did a postdoc there for about a year and a half before I left academia. So
I was Aberystwyth with, but anyway, thank
cool.
you.
Yeah, of course. All right, pause. Let me see the status of this. Nope. Carry on.
Okay. I was curious, what's your take on the term solar system? And like if you're watching sci-fi and they call another star system a solar system, or like a term like solar power.
Right.
And in terms of applying to other stars and suns.
That sort of stuff doesn't bother me. I think that because it's all rooted in, it's like we have our own bias, right? And if you're going to further confuse things, like that's a problem. Here's our display settings. And so for me, it's the most important thing is just to make sure you're getting that concept of the cosmological address right? Right? So that's the planets go around a star, which then goes around, which then, is in a galaxy, which then may be in a galaxy cluster, which is in our universe. It's the conflagration of galaxies and star systems that I get angry about. But if it's, solar power, it's all rooted in our language anyway, and I know a lot of sci-fi kind of gets around it because it's the Sol system, right? Star Trek does that. So Sol is our star. That's fine. But for me, the most important thing is just to understand the general address layout of our universe. Thank you. Thank you for your patience, everyone.
Hi, I am constantly amazed with your ability to communicate like really complex scientific ideas just so clearly and accessibly. So do you have any tips for scientists looking to do that in their own work? Like how do we become better communicators?
That is a great question. I feel like I bribed you to ask that. I didn't, but that was a great question. And so I would say for anyone who's interested, I really honed my skills working at a science museum, a science center, which I know are always looking for volunteers. So if you have any science background and you have spare time, which I know is few and far between these days, but I will say that is where I got the most experience. I was working there part-time. Obviously, most of it's volunteer work, but what I was able to do was for 6 hours a day, I was mostly fielding questions from the general public. And so that got me comfortable with saying, I don't actually know that. Let's look it up. and the museum I worked at was great because they would give us all kind of like little kiosks with laptops that we could literally look stuff up for people. So I got really comfortable doing that. But then also, I would start to get these questions and it would be like, black holes or galaxies or supernova or black holes and all of those. And you start to kind of narrow down 90% of the questions that people are interested in, the general public who doesn't necessarily have a science background, when they get to talk to an astrophysicist, what they're interested in. So for the stuff where it was like, I don't know, I would look it up, and then that question would keep coming back and coming back. And so, or looking up stuff in my textbooks from when I haven't thought about it in like 5 years, I can at least refresh that and then be prepared for those questions. So I would say like just getting out there and communicating with the public, doing panels like these, that was, again, I did the museums first before this, but I was rusty. It takes practice, and you have to go into it with the humility to be like, I am not a famous science communicator. I want to be, but I have to learn. And it really takes humility and practice and learning and adapting before, kind of get good. We have the laptop. Okay, pause, please. Hey! All right, so we're going to put a pause on questions. I apologize, but thank you all. Now, I'm going to start this. You might be prepared to stand back up again if these videos don't work. Can I just kind of run forward and make sure the sound works? All right. I haven't given my disclaimers yet. Oh, yeah. Since I won't go back to this, disclaimers. First of all, anything I worked on, you're going to see a little corner of me pop up because I don't want to be like, I'm totally bragging because this is like really good science, but like I want you to know that I am biased. So little Erin's going to pop in the corner for episodes that I worked on. I'm not trying to do a victory lap. I'm just full disclosure. And then the other thing, obviously there's too much, and we have already eaten through 20 minutes of my presentation, so we're not going to get to everything. I wish I could get to more. There's a lot of fun stuff. And then the last part is that if you are going on the Star Trek cruise, which I am discovering there's a lot of people here who are, you will see this full talk, hopefully in all of its glory, but just be prepared that there are going to be repeats. And then I'm going to test a video before I get to the rest of this. All right. Playing. Sound will come soon.
But then I said that
all right. Now we're going to learn stuff. We're doing this. Okay. Space-time. Who is familiar with the concept of space-time scientifically? Good amount. Okay. For those of you who aren't, I'm going to do a quick primer. Kind of talk a little bit about the history, and that's important because then I'm going to go through as many aspects as I can of space-time in Star Trek, and we're going to watch a lot of Star Trek, so I apologize. I think it's the greatest hits. I even had to narrow down some of my where I'm like, this is too much to explain, so it's going in the back. We will not have time for those, but I have them. And but first, to talk about space-time, most people kind of stop here when it comes to gravity. You learn about Newtonian gravity, where we treat gravity as a force between two objects that goes down as the square of the distance between them. Saw a couple people twitch, go, oh yeah, I remember that. And this held true for 99% of stuff. Like, that's why it's still taught. And it's still taught as if it's a force at the beginning. And then if any of you have gone on in physics, you will remember that moment where they said, oh yeah, so all that stuff that you spent years learning and getting memorized, they're like, all wrong. So Newtonian gravity held true for a long time. But the problem was, we were starting to get better at observing our universe and our solar system, and we discovered that Mercury's orbit does something weird. Mercury's orbit precesses, which means it traces out a flower shape as it goes around the sun. And for Newtonian gravity, there had to be something there to make that do that. It wouldn't just be going if it was the sun and Mercury. Telescopes are getting better. We're not quite seeing something, but they did the math, and eagle-eyed viewers might notice what they called that planet. This is an actual star chart from the 19th century where they have planet Vulcan in there because they thought that Vulcan would be pulling on Mercury to make it precess. But again, telescopes are getting better, and they realized that there was no Mercury there, or there was no Vulcan there. And that was because they could predict exactly where it would be from Newtonian gravity, and telescopes were good enough, and it wasn't there. So that's a problem. So this was a crisis for a few decades. Oh, okay, I thought I heard someone talk. That was weird. And so this was starting to be a crisis, and people were playing around with different ideas. In addition to this, there were scientists and actually more mathematicians who were playing around with the idea that our universe is four-dimensional, just purely from a math perspective. They were like, we can think of our universe as three-dimensional, forward, back, left, right, up, down. We can move in that space, but we also step forward in time at 1 second per second. So you combine this into 4 dimensions, and then that's that could be our universe. Now, scientists that wasn't really married with the whole gravity idea until Einstein came along and said, well, let's put mass there. Let's put a bowling ball on the trampoline and let's see what happens to the curvature of this space-time. And this is general relativity. So all of this is happening kind of within a few decades of each other, trying to figure out this space-time and then space-time plus mass, and then how that mass moves within our universe. So it's that trampoline, it's that sheet of space-time that we think about, and then we learn to play with that. And that's the science fiction aspect. So we're going to start off our Star Trek examples by a joke that is hopefully much funnier to you now that you've heard this explanation.
I said that frame of reference, the perihelion of Mercury would have processed in the opposite direction.
That is a great story. Quite amusing, Dr. Hawking. You see, Sir Isaac, the joke depends on an understanding of the relativistic curvature of space-time. If two non-inertial reference frames are in relative motion...
Do not patronize me, sir. I invented physics. The day that apple fell on my head was the most momentous day in the history of science.
Love it. Never stops being funny. In addition to this, right, we have these universal constants. Gravity constant is what you might remember from your Newtonian equation, and that is still a constant in our universe. Most of the time.
Down on Braille 4, we're gonna be hurt.
Yes. Your marvelous plan will not only tear the moon to pieces, but your precious ship as well.
You got a better idea?
Well, I would certainly begin by examining the cause and not the symptom.
We've already done that, Hugh, and there's no way to...
This is obviously the result of a large celestial object passing through at near right angles to the plane of the star system. Probably a black hole.
Can you recommend a way to counter the effect?
Simple. Change the gravitational constant of the universe.
What?
Change the gravitational constant of the universe, thereby altering the mass of the asteroid.
Redefine gravity. And how am I supposed to do that?
You just do it! Where's that doctor anyway?
So gravity. Gravity is important when we're traveling through space, but particularly with artificial gravity. Now, we've seen artificial gravity in all sorts of forms in science fiction over the years, right? We have the famous 2001 Space Odyssey rotating space station, which is also part of Ringworld and Mass Effect and all of these other sci-fi franchises. Star Trek's artificial gravity works because it works. And to be honest, there's not a ton of examples of how it works. All we know is we have a gravity generator. And if you're just going to go off of the shows, you're going to start running into trouble because they never explain it. The closest we got were the TNG technical manuals where they show a schematic of the gravity generator, which I love because it has superconductors in it. And if any of you remember, when superconductors were a huge deal and we were talking about how to explore the different uses for them, happened to be about the same time the Next Generation was coming out. So it kind of dated all of that in a really fun way. But yeah, they work very well. Thank you for asking. But we've seen other ways that we have generated artificial gravity in Star Trek over the years.
Magnetize.
Watching the boost ticks.
I intend to.
Now, you might argue that, is this artificial gravity? At least if you get the magnets to work just right enough that it feels like you're walking around, that's not a bad idea. But we've never, I don't know what that would feel like to be in 0G with my feet just magnetized down.
How are you doing, Mr. Wolf? Not well, sir.
Stresses me out so much. All right. And then this is another great example of the gravity generator that I love.
You're upside down, Ensign.
Yes, sir.
Care to explain why?
When I was a kid, we called it the sweet spot. Every ship's got one.
Sweet spot?
It's usually about halfway between the grav generator and the bow plate. Grab a hold of the hatch. No, on either side. Now, push off. Push off.
This is really awkward. Brace yourself.
Whoa!
Told you to brace yourself. All right, last clip that we had.
That was a run of approximately 10.1 kilometers.
Taking a run, it was a death wish.
You may be experiencing difficulty because I increased the gravity on this deck by 10%.
What?
Okay, so the way I see the gravity generators work on Star Trek, because turns out I've also had to answer this question a few times. We don't know quite how they're generating the gravity, but whatever they're doing, I kind of pull from Mass Effect, and I'm totally biased in this sense. But the way that Mass Effect generates artificial gravity on their ships, because they do actually try to explain it, no shade to Star Trek, because they don't have to, but they create localized gravity wells. Real hard to do. Don't know how we're going to do it. But the gravity wells are that dipping of space-time that I talked about. So when you introduce mass to space-time, it dips it down and it creates what we call a gravity well, which is really important to like how you launch off the surface of a planet. Or when I let go of something and it falls, it's falling down into that gravity well. So this is important to think about. This is just kind of a cool XKCD comic where they showed the relative gravity wells of all of the planets in our solar system. Super nerdy. But I put this in here so I would remember to talk about escape velocity, because I think that that's really important when we're talking about gravity wells. So the difficulty for us to get off of Earth is the energy required to crawl out of our gravity well. That's like the important, difficult part. Once you're out of it, then it's not require as much energy. We have Newtonian physics, which still holds up. If you're moving in a direction, unless something's going to stop you or point you in a different direction, you're just going to keep going. Let me see. Which clip is this? We'll find out. Oh, yes.
Report. We have entered a massive gravitational field, Captain.
There are no stars or other stellar bodies listed on our navigational charts. However, sensors indicate the presence of an extremely strong gravitational source in this vicinity.
Can you localize the source of the gravitational field?
I'm going to skip ahead from that one because it goes on and we don't need to start talking about Dyson spheres because I'm already short on time. But if you remember, that's the episode Relics. It does make you cry, so pace out when you watch that. But that's where Scotty's shuttle got trapped in the gravity well of the Dyson sphere, and he didn't have enough thrust or energy or fuel to crawl back out, which is why he hit himself in the transporter, yada, yada, yada.
All right, give me the bad news.
Magnetized ionic plasma in those fragments overloaded the ship's systems. It's like we were hit with an EMP. Warp cores offline.
What about reserves?
Backup power cells are down. Captain, it's all down.
But we're still moving? Momentum plus the Laperian gravity well.
But that means...
Unless we figure something out, first contact is gonna be us crashing into that planet. Okay, that's enough existential dread. Let's get back to work.
Brilliant. So good. So good. I will, because this reminded me, I do have one slide in here that has spoilers for Prodigy. Who cares? Anyone care? Sort of? I'll give you a heads up. All right. So gravity wells, which include slingshotting. So if you think of a gravity well, you might have seen this at a science museum. You have a bowling ball on a trampoline and you flick a marble. That marble is going to head toward it and then it's going to fling off in a different direction. This is actually how we confirmed general relativity back in 1919, I want to say, where we were able to see light getting curved around the mass of the sun during a solar eclipse. So the stars looked like they were in a different direction because the light was passing close enough that it was curved. So we use this science, this physics, to be able to change direction when we send stuff into our solar system. It's almost like a momentum transfer in a weird way. You get these objects close enough that they slingshot and they transfer momentum. So it's kind of like a collision. But if you remember, momentum is your mass and your velocity or your speed combined. And so you have a really, really, really tiny spacecraft moving really fast. It's going to go past a very, very massive, relatively slow moving planet, and that momentum is going to transfer. The satellite or the telescope is going to gain speed. It's going to change velocity. The planet will technically lose speed, but because it's so massive, it's negligible. And so that's why we use this slingshotting when we're sending stuff around the solar system. What it can also be used for is going back in time using warp drive.
We've done it before. Sure, slingshot around the sun, pick up enough speed, you're in time warp. If you don't, you're fried. Would you prefer to do nothing? I prefer a dose of common sense.
Can we make breakaway speed?
Hardly, Admiral. I cannot even guarantee we'll escape the sun's gravity. I shall attempt to compensate by altering our trajectory.
So my goal for this talk is for you, when you rewatch these, you'll be like, I get it now. That's pretty cool. Yeah, that's my goal. That's what you're going to walk away with. And gravity wells. Here's another. This isn't the Prodigy spoilers. It's just Prodigy, which you should all watch.
Oh, that does not look routine.
Oh, beautiful.
What exactly am I looking at?
Your course has led us into a binary system where the gravitational pull of an orbiting white dwarf is in the final moments of tearing apart a red giant.
A dying star. What a rare and exciting way to meet our doom.
This right here is why we shouldn't be in space.
Okay. Appears like we're still heading straight into it. Why aren't we changing course, Z?
It's not me. We are falling into the dwarf star's gravity well.
Then warp us out of here.
Okay, doing what you told me to do.
Just a friendly reminder. Using a warp drive inside a gravity well may result in unpredictable and dangerous side effects.
Right, I knew that.
Okay, she's back in the brick. Oh my gosh. What is that river of fire?
Trillions of tons of white-hot ionized gas about to explode.
That sounds worse.
What's the call, Captain?
I don't know. We've done everything you've said, and we're still fighting to get out.
That's it. What if we stop fighting and ride the shockwave? Let it propel us free.
Bingo.
You were reading my mind.
Now that is another lie.
Love it. All right. I am not going to talk about red matter. I am using this moment, and just a heads up, the sound might be a little loud on this one if you get a chance, so just be ready. But I'm just showing another favorite moment from this.
Sulu, let's go home. Yes, sir.
Kirk Engineering, get us out of here, Scotty.
You bet your ass, Captain! Captain McCoy, the gravity well has got us!
Go to maximum warp, push it!
I'm giving her all she's got, Captain!
Escape velocities. They don't have enough energy to get out of the gravity well.
All she's got, is it good enough? What else you got?
Okay, if we eject the core and detonate, the blast could be enough to push us away. I can't promise anything, though.
I do have the whole clip in there, but I don't have enough time to play it. But it's really cool. But the energy from the detonation pushes them out because they needed more velocity to get out of the gravity well. All right, but along those lines, the red matter created a black hole. So now we're going to talk about what black holes are. So black holes are singularities. And this is kind of, we see that term used in Star Trek as well. But this, again, was something that had been thought about for years as a concept and a consequence of general relativity and just space-time in general, that you would have a fabric, because this is a deep math joke. Any mathematicians out there, we love to divide by zero and see what happens. And so when they were like playing with the fabric of space-time, it was like, what happens if there's a singularity? So this question had always been there, like what happens if it goes to infinity or anything like that? And didn't necessarily have the other physics, the the astrophysics side of it to think about this, until we started looking at what the life cycle of a star is. Now, as we observed stars, especially in the early 1900s, we were seeing all these stars of different colors and sizes and shapes, and realizing, you know, these red giants are sort of a star at the end of their life cycle. I'm not going to go into the whole thing because that's literally like 2 lectures in Astronomy 101. But when a star dies, if it's massive enough, the radiation pressure and the gravitational pressure will no longer be able to stabilize each other, and that star is going to collapse in on itself. The outer shells will basically bounce off. They'll start to collapse and not be able to collapse any further. That's the supernova. And then what's left behind is going to be a neutron star, or if it's more massive, it's going to collapse because that neutron star can't hold up against itself. It'll collapse into a black hole, which is that singularity. So you think about pinching the trampoline and pulling it all the way down. And the black hole part of it is tying back to the escape velocity. It's the fact that your gravity well is so steep that your escape velocity is greater than the speed of light, which is fixed, and we can't change that. And so that's why we call it a black hole. It's just a really steep gravitational well, but there's no way we know what's inside, exactly what the topology of that is. There's a whole numerical relativity is what the field is called in astrophysics, where they try to mathematically model these things and compare it to what we see, and it is no joke. That is hard work. But the black holes, that's kind of the basis of where they come from. And of course, we see black holes all the time in Star Trek. But this is one of my favorite stories, anecdotes, examples ever. I'll let you watch the clip and then I'll talk about it. Remember this?
Captain's log, stardate 3113.2. We were en route to Starbase 9 for resupply when a black star of high gravitational attraction began to drag us toward it. It required all warp power in reverse to pull us away from the star. But like snapping a rubber band, the breakaway sent us plunging through space, out of control, to stop here, wherever we are.
Dun, dun, dun. What's awesome about that clip is this came out within a year of the term black hole being coined for the first time. So he calls it a black star of high gravitational attraction. Like I said, the idea of singularities, the concept of black holes had been around. That wasn't this Star Trek wasn't the first one to come up with a black hole, but black star, black hole, literally within a year of each other. I mean, with the time it takes to make a television show and the time it takes to get a paper published, you cannot really say which one came first, but the fact that it was like coincident, I just love. And it's very humbling to think how long ago that was and how used we are to the term black hole, that this was like one of the first time anyone had heard about that concept in the general public. Oh, there's going to be some serious mansplaining from Neelix here, so brace yourself.
Nothing I recognize, but then it's so hard to make out.
They may be trapped in the event horizon. Open a channel. This is Captain Catherine Janeway of the Starship Voyager to the vessel near the quantum singularity. Do you need help? Event horizon?
A singularity is a star that's collapsed in on itself. The event horizon is a very powerful energy field surrounding it. Why, once on a particularly dangerous trade mission to the twin stars of Kalota, I myself was almost trapped inside.
No response to our hail, Captain.
Can we tractor the vessel out?
No, the subspace interference is too heavy.
Captain, we're less than 3 light years from Ilidaria. They have
Okay.
technology.
The fact that this is like episode 3 of Voyager, they are already sick of Neelix. Like, cracks me up. And I do love Neelix. Like, I cry at the end of Voyager. Like, but it just, she's like, no, I'm done listening to your voice. Tuvok's already interrupting him. It's hilarious. But yes, Event Horizons. And as condescending as Neelix is in that moment, he's actually explains it really well, which is why I use that clip.
You're sure it's a black hole?
A class 4.
According to the Vulcan Star Charger, people have surveyed more than 2,000 of these things.
That's correct. But none of them were part of our trinary star system.
How close can we get?
The gravitational shear between the stars is extreme. We'd have to drop to impulse, but we should be able to approach to within 5 million kilometers.
Close enough to get some nice pictures.
So what I love about this clip is they talk about it being a trinary system, which is why it's like unstable. And even early 2000s, and I remember because this is about when I was in college, they thought that binary star systems, so two stars and planets going around them, couldn't exist because it would be too chaotic of a star system. Since then, we've discovered star systems with binary stars and planets going around them in various configurations. But it just, again, goes to show like how quickly the science catches up to and surpasses some of the stuff that we see in these shows. Yeah, humble brag.
My newest obstacle is the presence of a nearby black hole.
Atmospheric density is decreasing. I believe the singularity is advancing its accumulation of substellar material.
Do you ever speak in plain English?
The brown dwarf we're hiding inside is being sucked into a black hole.
We stay, we go with it.
Precisely.
And we can't pop our heads up to see if it's clear to leave. They could see us.
Without long-range communication, we cannot even send a probe.
How much time before we can't escape the black hole's gravity?
1 hour, 32 minutes, and 48 seconds.
So this is a perfect example because even though there's a little thing of me in the corner, they don't always listen to the science advisor, and that's fine. But I want you to know that if you catch stuff and you go, oh, nope, didn't like that, I'm fallible. I make mistakes. That's fine. I will never make the mistake of saying it's getting sucked into a black hole because things don't get sucked in. They fall in because it's a gravity well. However, you flag it. You say it should be falling in the dwarf stars, but the outer layers are falling in. And then everyone else who's like part of the production is like, well, that doesn't make sense. And that's not scary enough. And it feel like it should be getting sucked in. And the story and the pacing and all of the scariness in the moment and the time you have to explain it supersede the technical scientific terms. So we let it go. We let it go. And I sleep at night perfectly fine knowing Spock says that you're getting sucked into a black hole. And if you want to take it a step further, La'an did specifically ask for simplified language. So Spock could just be talking down to her. So, but you can think of it however you want. That's my in-universe explanation.
Captain, Voyager 6 disappeared to what they used to call a black hole.
It must have emerged on the far side of the galaxy and fell into the machine planet's gravitational field.
All right, now we're moving into the next phase, which is wormholes, I think. No, first we're going to talk about artificial singularities. Because I will talk about wormholes. Yes, I definitely have time. Artificial singularities power Romulan ships. Do not have enough time to explain it right now, but it is their version of warp drive. The way I think about it is they create an artificial tiny little black hole in their engine that either, you can think about it, that it's like pulling, like the ship is constantly falling into, which is able to change the speed of it, or the mass energy that's radiating off of it is powering the ship. The explanations and details they give is a little iffy, but really it's the energy that it's creating, which technically, and I've had this question before, people ask like, well, why weren't the Romulans affected with the burn in Discovery? And it's like, well, you still need a lot of energy to create an artificial singularity in the same way you need a lot of energy to create a warp bubble. So who says they still aren't using matter, antimatter mixed together, create artificial singularity? We're going to skip that, talk about warp drive. Warp drive, our favorite thing. So mathematically, probably most of you heard this, warp drive is possible. It's the idea, and I've talked about space-time and gravity wells, so hopefully you have some image in your mind with that, that you can go a certain speed, you have mass, so you have a gravity well, your starship, and you're limited in how fast you can go because you have that mass. The lighter you are, the faster, the easier it is to move through space-time till you have no mass and you coast in a straight line, which is the speed of light because photons have no mass. But nothing in those rules says that space-time itself can't go faster than the speed of light. So the idea behind warp drive is you build a bubble around your ship. You can see where the ship is, it's still normal space-time, but the bubble is pushing the ship faster than the speed of light because space-time itself can move faster than the speed of light. It's just the mass that's on it that doesn't let you. I know it's a little brain bendy, so I apologize. I have a lot of videos and a lot more detailed explanations on this if people want to look it up. But mathematically, it works. And people have tried to figure out how much energy it would take. Again, I kind of alluded to this with creating the artificial singularity. If you don't have the mass to create a gravity well, Einstein also came up with this thing called energy mass equivalence, or E equals mc squared. So you could use an equivalent amount of energy to dips to bend space-time. Now, this is something we physically don't know how to do yet, but we have now, with gravitational wave detections, actually detected the motion of space-time itself. So we're getting there. It's baby steps. It's baby steps. But the first calculations that they did to figure out how much energy would be required to actually bend space-time this much to power warp drive was all the energy. Ever. Not great. They've since made modifications. The last I heard, which was years ago now, I've tried to keep an eye out. I might have missed it, but the best I've seen is the energy equivalent of the mass of a semi-truck. So you take a semi-truck and convert that mass into energy. That's how much energy you need. But recall that nuclear bombs are the release of the energy stored in a teaspoon of matter. So scale that up. That is why he drinks, which I'm fine with. I would too. But obviously, warp drive, lots of fun stuff we can play with. I like to think of that, you bend space-time around your ship, it moves you through. You want to exponentially increase your speed, you build another bubble around that bubble. That's your warp factor 2. Build another bubble around that bubble, warp factor 3, as we have seen.
NX control. I thought we built a warp ship so we could go to warp.
Maintain your orbit. We're trying to run down a problem with the stabilization protocols.
I just saw Italy go by again. If this is going to take much longer, maybe you can send up some food.
Can I get you?
How about some of those deep-fried mushrooms from the 602?
I'll send Ruby up to take your order.
We are clear on the stabilization protocols. We start countdown at 30 seconds.
All right.
Good news, AG.
I'm going to skip through this because we don't have time for all the tragedy and all this stuff that happens because it's very stressful. But he goes to warp factor 2 and the ship bumps and all that fun stuff because I'm trying to get to this episode, which is my favorite.
We're trying to break the maximum warp barrier. Nothing in the universe can go warp 10. It's a theoretical impossibility. In principle, if you were ever to reach warp 10, you'd be traveling at infinite velocity.
Infinite velocity? Got it. So that means very fast.
It means that you would occupy every point in the universe simultaneously. In theory, you could go any place in the wink of an eye. Time and distance would have no meaning. If Voyager achieved warp 10, we could be home in as long as it takes to push a button.
Ow. So, Threshold. We need to talk about Threshold. So, if you haven't heard, especially the lovely Tawny Newsome is here. I was privileged enough to be a guest on her podcast, The Pod Directive, with her and Paul F. Tompkins. And they asked me to pick an episode to talk about, and I picked Threshold. And Paul F. Tompkins is convinced that I have Stockholm Syndrome with this episode. But here's my argument for Threshold. It's really good until Tom Paris's tongue falls out. It's a really good episode until the lizard evolution happens. And I think the way they talk about warp drive and this theoretical limit is brilliant, right? Because I talked about that warp factor 2, warp factor 3. There is an idea that you would eventually, because you're exponentially increasing your speed and how much space-time is required, you would be wrapping all of space and time around your ship and exist in all places at once, as they explain here. Another thing about warp factors and warp speed and how fast is warp 1, how fast is warp 2, the way I see it, and I really do stand by this, is that it's totally dependent on your ship, because the lighter ship, you got your tiny little Intrepid class, your science ship that could, is not going to require as much energy to obtain warp factor 1 as a Galaxy class ship. That thing is massive, and that's going to require a lot more energy to create. And so they're not like a universal warp factor 1 equals 1.8 times the speed of light, because it's going to be different depending on all the ships that you have. So that's my official take on it. That's kind of how I've seen things.
You have made a very serious accusation. I want you to explain it.
Captain, according to our research, warp fields cause a dangerous reaction in this region of space.
Our planet is already being affected. We have measured large gravitational shifts throughout our system.
If something isn't done, our planet will become uninhabitable.
Okay, so how many of you had thought about this episode as I was talking about warp drive? Yep, couple people. Okay, so this is Force of Nature. This is where they talk about warp drive through a corridor, the same location all the time, eventually starts rending space-time. I love this idea. The big problem is that space is very, very big. So the likelihood that one warp path is going to be the same as another one is very unlikely. But this episode does a good job of talking about the volatility in this particular region. There is actually one good spot to travel through, so everyone kind of takes this spot. And the way I kind of see it is it's like a sweater that's just kind of being rended constantly, right? And so it just, all that fabric starts to loosen and starts to become hard to go to warp and eventually like unstable. This is other ways that they talk about it, but the general concept, like, I think is really, really good. Wait, I am so running out of time. I'm going to blast through the greatest hits of wormholes. So wormholes, as they were talking about like black holes that, with the V'ger example, a black hole that ends up somewhere else. And wormholes, the topography of wormholes, topologically, are almost identical to black holes in the sense that you're going to have a really steep gravity well. You're going to get spaghettified if you try to go through it. It's not going to be great. But it's this idea that you could have our fabric of space-time, which overall we see as flat. The best research we've done, okay, the universe is flat. But if you think about like taking toilet paper or something, crumpling it all up and just throwing it down on the ground, it's gonna overall lie flat, but there's gonna be bumps and ridges and parts where it folds over on itself. And that's this idea where you travel on the surface is gonna take a long time, but you might be able to punch through and find a shortcut. And there's like so many good examples of this, especially in Voyager, because they're trying to shortcut a massive distance that is going to take a lot of time. They're constantly looking for wormholes. I got to like figure out what all these clips are. I have a lot of wormhole clips.
The readings from the Barzan's probe of the wormhole are quite impressive.
Barzan wormhole, they find that it's unstable and it like flaps around like a dog's tail, and then they end up, the Ferengi is like the second part of that episode in Voyager, and it's great. Love it. That's called The Price. False Prophets is the Voyager episode.
Now, as we discussed in yesterday's lesson, the wormhole was discovered by Commander Sisko and Lieutenant Dax earlier this year. Does anyone know what makes this wormhole so unusual? Jake? It's stable? It's stable. That's right, Jake. It's the first stable wormhole known to exist.
Kai Wynn walked in. Boo! First sighting of Kai Wynn. Boo! Yeah, so what I love is the Barzan wormhole, The Price, that episode, they're pitching that wormhole as stable. Like they're trying, the Ferengi are going to like run tolls on it and it's great. But they realize that it's unstable. And then we have the Bajoran wormhole, which is a naturally occurring wormhole that does connect the alpha quadrant to the gamma quadrant. It's just, yeah, that's the main parts of that. Okay. I'm not going to play this whole thing because we don't have time. Mostly, I cry in this episode.
Here, people. Take us through it again, Mr. Barclay. One step at a time. Maybe it'll spark an idea.
We've got our itinerant pulsar. We've got our interdimensional transponder array. How do we get our wormhole?
Is one going to keep us up all night?
We know we can produce gravimetric energy, but can we do it at levels high enough to create the singularity?
We're talking about a massive subspace reaction.
Maybe.
Okay, I'll stop it there. They land on needing a micro wormhole, and then they're able to communicate with Voyager, and it's beautiful and it's amazing. And this is also the episode where I realized I want to be Captain Janeway. I am Barclay. I would 100% have a holodeck program where I just hung out with the Voyager crew all the time. And then this is, I think, the episode I was really going for.
Captain's log,
Perfect.
Stardate 48579.4. The crew has been scanning constantly for anomalies that might help us shorten our journey home. Ensign Kim has reported an exciting discovery, a subspace disturbance which may be a wormhole. Let's see what you have, Mr. Kim.
There.
It's registering only on subspace bands. We don't even have it on long-range sensors yet.
Verteron emanations. Tunneling secondary particles. It certainly looks like a wormhole.
But is it stable enough for us to enter? And if it is, where does it lead? There is, of course, a 75% chance a wormhole will not lead to the Alpha Quadrant.
Very true. But you can also say there's a 1 in 4 chance it will. Those aren't bad odds. Any analysis yet, Ensign?
Too far away. We'd have to be within 1,000 kilometers to get a detailed analysis. That would mean a significant course change.
Well, Mr. Kim, if there's even the possibility of finding a wormhole, I think we can afford a detour.
I'm going to keep playing here because this is really cool.
Evacuation procedures.
I suggest we delay that for the moment, Captain. I'm afraid I found the reason for the unusual phase variance.
What is it?
Captain, what year is it?
Okay, I'll stop it there just for time. But what I love about that episode, this is Eye of the Needle, season 1. Voyager comes out of the gate swinging. Can we just say, like, first, I've used like 3 episodes from the beginning of season 1. So this is Eye of the Needle. And what I love about it is they talk about the fact that a wormhole will connect both places in space and time. We didn't really ever address that with the Bajoran wormhole, that you end up in a different time as well as a different place. And maybe the Bajoran wormhole, I mean, it was like the prophets are involved, whatever. So that might not necessarily be the case, but this one explicitly said not only does it connect to the Alpha Quadrant, it connects to a different time as well. And I cut it off at a point. If you haven't watched this in a long time or have never watched it, you should watch this episode because it's very, very good. And then I will end on this part because I'm going to brag. But this is my favorite episode of Star Trek ever. It's called Counterpoint. It's my favorite episode for so many reasons. This is one of the greatest scenes, I think, in Star Trek ever. To give context, they're looking for a wormhole that keeps popping up and disappearing, and they find this expert who's just going to be a pure classic academic.
Obscurity? I've discovered over 60 astronomical phenomena. Not worth the sensors they were recorded on. Oh.
There's no need to insult the man, just because he doesn't know how to find an interspatial flexure.
Ooh. Interspatial flexure? Why didn't you say so in the first place? He said wormhole, a layman's term that covers any number of phenomena. I am familiar with a certain anomaly that could be categorized as an interspatial flexure.
Where is it?
Actually, a better question would be, where is it now? It's really quite interesting. The aperture of the phenomenon, which I prefer to call an intermittent cyclical vortex, is unfixed. It manifests infrequently for only brief periods of time and in varying locations.
So good, so good. So this is my last little braggy part that I want, because I love that episode. I love that scene so much. We had this opportunity. This is a spoiler for Prodigy. I'm going to end on this, so dart out of the room real fast if you don't want to see this.
It was sent from another time, 52 years from now.
Half my crew's gone, but I'm trying to hang on.
How is that possible?
The hologram advisor's last act was to duplicate the parameters logged in the original wormhole Captain Chakotay was lost in, thusly creating an interspatial flexure to approximately the same space-time coordinates.
Yeah! I got interspatial flexure in there a second time. So on that note, thank you all. I appreciate it.
Hi, this is Michael Shanks, and you're watching Fandom Spotlight. Be sure to like, share, and subscribe. The fate of the universe may depend on it. Oh, and have fun, and follow your fandom.